My name is Morgan Lee. I'm a second-year PhD student in the computer science department here at WPI, and I do research in an educational technology lab, more specifically focused on educational technology and reinforcement learning for education. So this project was about contextual bandit algorithms and supplying different features to those bandit algorithms to see if we get better recommendations. So I'm going to break down those terms for you. So a contextual bandit algorithm, imagine you are in a casino. There are three slot machines right in front of you. You can pull the arm on each one, and each has a different chance of giving you the jackpot. How do you decide which slot machine to go for? The general idea is you pull each slot machine arm a predetermined number of times to figure out which one is more likely to give you the jackpot, and then you go with that one. That is the multi-armed bandit problem in reinforcement learning. The one thing that's different with what we're doing is we use contextual bandits, which that's like if for each slot machine, it might have a different distribution if a man or a woman pulls the thing, or if you pull it at a certain time of day. So you take in context of the situation and factor that in when you're calculating rewards. So what I did with this project, so in Assessments, there are, Assessments is a free online educational platform used by middle school math students across the country. And most problems in Assessments have at least two educational supports. So hints or explanations that a student can request at any time to get instruction. So it stands to reason that some of those hints and explanations might be better for some students than others. Some students might need things to be explained very abstractly. Some students might need problems to be broken down into parts. So how do we figure out which hints to give to which students? The answer is reinforcement learning. Putting it back in the jackpot example for a second, the different arms that we can pull are different hints or explanations that we can give to the student. And what we want to do is we want to give students the hints and explanations that are more likely to have the student learn. And we measure that by whether or not the student looks at a hint and then gets the next problem in whatever homework assignment they're doing correct. So all of this is work that has been done in Assessments previously. And the context that this bandit is taking in is a bunch of computed averages that we compute across the entire Assessments database. So these can be features at the user level, like a user average correctness. How likely is this particular student to get a problem correct on the first try? They can be problem level features or like tutor strategy level features. So I want to focus more specifically on those features and what they're trying to approximate in our models. So think about that user average correctness for a second. That, in our model, is kind of a stand-in for prior knowledge, right? That number is telling the model how likely a student is to know something, right? It's how much a student generally knows. But if a student is doing the first few problems on a new skill, like say the student is learning something for the first time, that number is going to be somewhat misleading, right? Because they don't know the thing that they're trying to learn. So using user average correctness as a feature in that particular case, it's a messy approximation at best. This is where other models from the educational data mining community come in. And the one that we used for this project specifically is called Bayesian knowledge tracing. BKT is a machine learning model that predicts, based on a sequence of correct and incorrect answers, whether or not the student will get the next problem of a particular skill correct. So we want to try giving measurements from BKT, predictions from BKT, as a feature into this reinforcement learning model. Now, the problem is doing that on a system that is live takes a lot of work and a lot of energy for a benefit that isn't necessarily there. So we wanted to see if the idea had promise. We did a simulation based off of data that was collected in Assessments, because sometimes if a student sometimes students receive hints at random, right? If there are 2 or 3 supports for a particular problem, students might get one that was randomly assigned to them. So what we did was we grabbed all of the examples of a student getting a random student support from the past 2 years, and we used that as the base data set to simulate our Bandit agents doing a series of recommendations, right? And we tried that with 3 different feature spaces. One, just a random model to use as a baseline to compare things to. One, which was just the base model with the standard feature space that I described before, and one using BKT prediction instead of that user average correctness feature. And we found that in simulation, the BKT models, the models with BKT as a feature, tended to outperform the models that did not. This figure here is a bit misleading. For each feature space, we did 5 simulations, and each simulation was 1 million recommendations each. This figure is just the confidence intervals of the averages of those simulations. But if you look at the difference between the means, our findings were significant. We did find that, at least in simulation, supplying better features here meaning a feature that is more theoretically supported than just an average, the recommendations that the models give tend to be better. We're looking to do an empirical study of something like this very soon.